Yeah. Okay.
There we go.
So, yeah, it was December 2012, and so at that time I was talking about supersymmetric dark matter and the impact of the LHC. It was still, there were Higgs events at the time, but it wasn't announced that Higgs, it wasn't a discovery yet. There was just an indication.
December 2012?
Yeah.
The Higgs was discovered in July 4th, 2012.
Well, it was still, at least that's the way I had it on the slides, the apparent discovery of the Higgs. It wasn't, it was...
Was the official discovery?
Is it 2012, not 2013?
No, it was
Okay,
4th of July.
2012, okay.
I was there.
Ah, yes.
I remember.
So, anyway, completely different subject, 12 years later, talking about mostly reheating, the processes of reheating coming out of inflation. And I'm going to, in the beginning part of the talk, stress the relationships between supergravity and the Starobinsky model, which is based on R plus R squared theory of gravity. So I'll be going through all of that. That'll be the first half. And second half is on particle production, and sort of is a little bit more similar to what I spoke about in Bella Horizonte. So just, okay, I'm not going to go through a lot of detail on supergravity, but from the practical point of view, and for constructing models of inflation, you need the scalar potential. And the scalar potential in supergravity is derived from a Kähler potential, which is G, which in turn is defined by two functions. One usually called the Kähler function as well, and that determines the kinetic terms of the scalar fields as well, and then a superpotential which contains all the information about the interactions. So you have an expression like this one, which doesn't tell you a lot. When you plug in for G, you get a little bit more information. If you know something about supersymmetry and supergravity, then one thing that jumps to mind here is the fact that there are two terms with a relative sign. In global supersymmetry, which has to be broken, supergravity has to be broken as well, because we obviously don't have evidence for it. In global supersymmetry, the order parameter for breaking would be dw d phi, and none of this would be here. This is all in Planck units, so if I send m Planck to infinity, these terms wouldn't be here. The exponential would be 1. You would just have the absolute value of this thing squared. Supersymmetry is broken, you necessarily have a cosmological constant, okay, which would be of order the supersymmetry breaking squared. In supergravity, you have the opportunity of breaking supergravity and still canceling the cosmological constant. So you can still set it to 0 or fine-tune it however you need to do.
So the cosmological constant is 0 without breaking supergravity and 0 after breaking supergravity?
If you break it in an appropriate way, right? So I mean, so you can write down a superpotential such that this is 0 with the supersymmetry broken. The order parameter now is that this term has to be non-zero, and so if you can arrange it, it's still fine-tuning. I mean, it's still fine-tuning, yeah, of course. So largely, this kind of framework can be dangerous for building models of inflation. It's usually called the Ada problem, and the way to see it is that whatever this quantity is, which is going to be of order the Hubble parameter, so if there's some vacuum energy density which is driving inflation, this is going to be about that size. But all scalar fields have this thing sitting out in front of it in minimal supergravity, so with k equaling to phi phi star, you can see. Then if you expand that exponential, you'll have something like 1 plus phi phi star, and then everything that follows would then be a mass term. So you would typically get masses which are of order the Hubble scale, and then you don't inflate. So that people always claim that there's a problem in supergravity.
This is called the Ada problem?
That's called the Ada problem, yeah.
Why Ada?
I'm not 100% sure. I think Ada, the slow roll parameter, which is going as V double prime.
Yeah, the second derivative is the same order.
Yeah, But I'll mention it. It should be the same
The
meter.
Newton field in this case is what? The scalar component?
I will get there. That comes later. So no scale supergravity is usually written in a very specific form for the Kähler potential. I mean, you can still generalize this, but so now so the phis are still, you can refer to them as matter fields. They will have more or less canonical kinetic terms coming from this, and here T is usually associated with the volume modulus in string theory, and it's been argued that this form of the Kähler potential is what naturally comes down from in the 4D reductions. So there's a paper by Witten long ago, and
Why is it called the no scale?
so no scale is because when you actually then derive the scalar potential, if you didn't have a super potential added onto this, the potential would just be zero. It's just the so in fact, even if you take this away, if you start with minus 3 log t plus t star, and that's your theory, you get a completely flat potential, and so there's no scales associated with it. If you add a superpotential, then you get something that looks like this, which again now starts to look like global supersymmetry. You can still arrange the cosmological constant is canceled, and so it looks like that when k is fixed. I'll get to that a little bit later. So this is probably the worst slide in terms of being technical. So this is the original supergravity Lagrangian. So a lot of terms. This isn't even all of it. This is just there's. Huh? Yeah, it's cut off. Probably even the parentheses don't close. I don't know. It's much longer, but I don't need the rest of it. I just need a few terms to sort of point to, and that's all. So what do I want to point to? I want to point to this one. This is R. This R is the Einstein scalar curvature. So phi R. So we're starting out not in the Einstein frame, if you want. We're in another conformal frame. And the z's here are the scalar fields, or what I called phi before. This phi is a different phi. This phi is actually related to the Kähler potential in some way. It's a different notation. Kähler potential here is minus j, so you'll see some j's in there. This phi is e to the j over 3. The superpotential is g, which is there as well, and this is introduced a little bit later. So these are now the scalar fields, and so this is some kinetic terms of the scalar fields. There's some more kinetic terms for the scalar fields here. All the interactions, the scalar potential is sitting there and there. When you combine everything, you'll get to what I showed you before once you do the conformal transformation to get rid of this phi r. So that's what I say here. You take that one term, and what you want to do is you want to get it to the Einstein frame so that the coefficient of r, e is like square root of g, but so this is, you just want properly normalized Einstein-Hilbert action, and then you get some other pieces that look like a kinetic term of scalar field. Okay? And so this is essentially d mu k that's sitting there, d mu k squared. So once you do all that, then you get a Lagrangian, and the kinetic part of the Lagrangian just looks like R, so Einstein gravity, and now you see that the derivatives of k determine for you the kinetic terms of your scalar fields. And your conformal transformation, so here, I guess I didn't write it, but g mu nu goes to e to the 2 omega times g mu nu, so standard conformal transformation, and in this particular case, the conformal factor 2 omega is given by minus k over 3, or this phi that was in the phi that's sitting there in front of r. Okay. And then you would get, if you plug everything in, you actually do get this a little bit.
This still is non-canonical normalized, right?
Yeah, so Kij, so if Kij is phi I star, then it is canonical. If it's in no scale, it's not canonical, that's right. Yeah, not necessarily all, because when you have multiple fields, and you can't necessarily simultaneously do it, but that's, okay. It doesn't matter. So, okay, again, just for reference, the Kremer et al. Phi, if you choose that, you get this K, which is ZZ star, and you get the canonical, so that's minimal n equals 1. No scale, your choice of phi would be just Z plus Z star, and then you get a K that looks like this. Okay? And this phi ZZ star in this case is 0, and then you get V equals 0 as well, okay? Without a superpotential. So these are special in another sense, is that these are maximally symmetric in field space. So you have a metric in field space, and now you're maximally symmetric, like say de Sitter in physical space. You have a Kähler curvature, which is a constant now. Okay. So that's sort of the basis for that. So now I'm just going to say a few words about how we construct some models. Okay. So you need to pick a superpotential, and we started out with something general, but Holman, Ramon, and Ross back in the early 80s said, oh, if you pick something that looks like that, very simple, single field, some mass scale, you plug it in, what you plug in, you get a mess because the expressions quickly get out of hand, but you don't care. You can expand around the origin, and you get something like this. The potential looks like this. So the idea is that, for pieces of the universe where the inflaton, so phi here, as we call it, the inflaton is sitting here, it will eventually roll to the minimum, and during this flat part, you would get inflation. So that's the basic idea.
This is not a no-scale model?
This is not a no-scale model.
The mu is the scale, right?
No, but that no scale is broken as soon as you put in the superpotential. So the no scale is referring to the form of the Kähler potential.
The mu is basically a free parameter.
The mu is a free parameter which is fixed by the CMB.
Right.
Okay, I'll get to that as well. So this was, at the time, this was sort of dropped because everybody was thinking about how you do your initial conditions. You should do your finite temperature corrections. Remember the old picture of phase transitions. The finite temperature, you compute something, so you get T squared phi squared, and then the universe cools, and then you get the zero temperature potential, and you move on. So you can do that here, but it doesn't give you, the finite temperature minimum isn't at the origin. It's like somewhere here or something. And so people say, well, okay. Nobody worries about that kind of setting up of initial conditions anymore. You just assume the universe is at T equals 0 from the start. And then you don't care. You say, well, still, why would you pick here? You don't even care about that. So long as there's some region here in the universe that's sitting here, that will expand exponentially and completely dominate everything else. So the pieces that are sitting anywhere else are completely irrelevant. So it was a big shift in the way people thought about it originally. And so then you can say, oh, but then this potential is good again, right? If you're not worried about the finite temperature. So you can do something similar in no scale. Again, pretty simple forms of the superpotential. Two different ones which give you essentially the same scalar potential, which isn't 100% exactly the same as the previous one, even though this is exactly the same figure, but you wouldn't notice the difference. And one is depending on what is actually fixed. There's getting an expectation value K or T.
So you're calling no scale.
Again, I'm calling it no scale because the K that's used to derive this is of the no scale form.
You don't need quotation for K.
No. K is just that.
It's the kinetic.
So what's one of the most important things that are coming out of inflation is the density fluctuations. So here, so I'm writing now here, I'm jumping ahead a little bit for a very specific form of a potential, Starobinsky potential, which I'll come back to. Maybe I should have put this a little bit later, a few slides later, but doesn't matter. So this is Starobinsky potential, and I'll explain this in a minute. There's the functional form. But what's important, the lower part here is general, is you want to look at the expectation value of, say, delta rho over rho squared, and look at the power spectrum for those density fluctuations. And so you can define it this way. It's usually expanded out something that looks like this. this AS is the normalization of the power spectrum, and so that's what's fixed by CMB observations. And the dependence on scale is given by, usually called the tilt of the anisotropy spectrum. And here you have the slow roll parameters epsilon and eta. So if V double prime is big, which means you have a large mass squared, then it's difficult to have inflation. So NS, this tilt, going back, even back to the 70s, it was believed that it should be 1. It should be at least very close to 1, based on arguments from Harrison and Zildovich. If you want to get structure, it should be, if you don't want to overclose or underpopulate, NS has to be about 1. And that was actually a big problem because you need this to be on, this power spectrum to be well defined on scales which now appear to have been much larger than the horizon. And so you say, how do you have a power law power spectrum on scales that are acausal? And so that was again one of these things that had to be anthropic, because otherwise there was no explanation until you get to something like inflation, which tells you that no, it's all causal, and these scales get pushed out of the horizon or our apparent horizon, and it's calculated.
Then comes back.
Hmm?
And then comes back.
And then comes back. So this is something that can be calculated. R is the tensor to scalar ratio, which is another important observable. If you compare the power spectrum due to the tensor fluctuations, these are the scalar fluctuations. And so this is a picture, this is a relatively old picture. Here you see a bunch of different models and the observations in the NSR plane. Okay, and I'll show an improved version of this in a short bit. Here you have the same thing I showed you before. So for these simple models that I showed that looked like 1 minus phi cubed, you can compute epsilon and eta, and the problem is for those models, epsilon is tiny, so R is also very tiny, but NS is 0.928. Now when those models were written down, didn't care, because they were 928, you could say at the time, was close enough to 1, but you see 928 would be somewhere here, right, would be badly excluded. So largely these models were tossed. As you see, the quartic chaotic inflation model, so phi to the fourth isn't even shown, it's even higher. It's at about 0.27 or so in R, and here you have the quadratic chaotic inflation model. It's also excluded. And okay, that was the big controversy with the bicep result, and but it was already in conflict with WMAP at the time. And so what you see here at the bottom is the R squared. Here it's called R squared, but it's really R plus R squared. It's the Starobinsky model is the one that's sitting here that looks good. And so a lot of people have started to concentrate more on that type of a model. So R plus R squared gravity, so just to back up a little bit, how did Starobinsky go about this? This was actually before Guth's inflation, so he was not trying to solve the problems of inflation because they weren't thinking about it in those terms. He was actually trying to get rid of the singularity, and he thought if I have an R squared term, there should be no singularity. And you can understand that when the curvature is very high and the R squared term dominates. If you have just R squared gravity, that's actually just de Sitter space. It's just pure R squared gravity is just de Sitter. So he thought, okay, you're starting with de Sitter, and somehow eventually the R takes over. And so now, okay, here's the definition of the e to the 2 omega. You do the conformal transformation. You can define effectively a Lagrange multiplier to get rid of the R plus R squared, and you run it through the machinery, and you get your action now in the Einstein frame. So you have just R, you get the appearance of a scalar field, and you get a potential. Okay. You have a new degree of freedom, which was coming from the R squared contribution. And so this functional form, this potential, is the Starobinsky potential, which is what I showed you before. So I left out all the steps here. Some of those steps will creep in a little bit later. And so just remember, this thing here is just a perfect square. Here I've already defined the canonical scalar field there. So, okay, so the top part is the same as what I showed you before, which is probably why that happened. You can actually get all these things analytically, the slow roll parameters. And so AS is something that's measured by the CMB. So that was the normalization of the power spectrum. That can be written in terms of the potential and epsilon, which you can also write down analytically. And so now you can find what that mu is, the mu that's there, or the capital M. And that's about 10 to the minus 5. This is all in Planck units. So this is 10 to the minus 5 or 10 to the 13 GeV for about 55 E foldings. And you can compute NS and R, and that's why it sits there right in that nice spot relative to the observations. Okay, so that's Starobinsky. Oh, here we go. So this is the modern version. So this is now using Planck 2018 data and some extra observations. I think it also has the Keck observations here. And so the upper limit is about 0.036 at 2 sigma. And here you see the Starobinsky model here. Just look at the alpha equals to 1. I think I'll mention alpha a little bit later. It'll come up. But for now, the Starobinsky model is just this one. And these other lines are, this depends on the reheating temperature. So this is a reheating temperature of 100 GeV. I think this is a reheating temperature of 4 MeV, just so that you get nucleosynthesis. This is a reheating temperature of about 10 to the 10 GeV. It's labeled as 100 GeV, but that's 100 GeV gravitino mass. So this is so that you don't have a problem with gravitinos. You have to keep the reheating temperature below about 10 to the 10. This is a reheating temperature of about 10 to the 5. It's labeled Y equals to 1 because of it's the coupling of how the inflaton decays. That'll come up a little bit later. And so N equals to 60. So normally people write the line here, the little bar between 50 and 60. 60 doesn't make any sense for the Starobinsky model. You just can't have 60. Yeah. Why? Because you would need a reheating temperature, which would be like a non-perturbative. There's not enough energy to get a reheating temperature high enough. I think I'll have a plot that makes that a little bit more clear. But you can't, in Starobinsky, you can't get N equals to 60. N equals 50 is okay, but even lower than 50 is also okay. It's in the calculation of, because when you're calculating capital N, you have to know what the equation of state is, and the reheating temperature is determining the change in the equation of state. I don't know if I've written down the
After inflation, right?
reheating is after inflation, but what you care about is the evolution towards the end of inflation. So you care about the shape of the potential, and you care about how the equation of state is changing. So, and you have to match it up eventually to a particular scale that you're observing on the sky, and that scale. So this scale is where the last 50 or 45 E foldings takes place. So here it's labeled as XI, and then eventually inflation ends when X is about order 1. Again, all in Planck units. I don't know if I have the formula I've written down, but we'll see. I'll have a plot, and the plot might help. So now you can ask, okay, how do you include matter in your Starobinsky model? So you could just say, and by matter here, I'm just going to keep it, with most part, I'm going to keep it simple, so just add a scalar field, which we can associate with the Higgs. Okay? So you could just say, take your R plus R squared, and you add the Higgs. Okay, that's fine. Now you do the same steps, and you do all your conformal transformations. So here's what we had before, and now you would have some extra pieces. The Higgs would no longer be canonical because you would have the e to the e to the minus 2 omega. Here you would have an e to the minus 4 omega sitting in front of the potential of the Higgs. Okay. You can still do an expansion, so you can simplify all that to just look at how now this, it's sometimes called the scalaron because that's the field that came from the r plus r squared, or the inflaton because that's what it's really doing here. And so you can write down the pieces that you care for, the decay of the inflaton and reheating, and so that's these, actually it's this piece that's dominant, and because this is going to be small, right, because this is going to have the Higgs mass squared here. If you're looking for phi to Higgs, this is going to be small, so the decay rate is really coming through the kinetic terms. And remember, this m is the Starobinsky m, so this is 10 to the minus 5 in Planck units. Okay, nh just the number of Higgses that you have. So standard supersymmetric model, you would have 4 scalars here. And
what is the mass of phi?
the mass of phi is actually is m.
Is m?
Is actually m. So it's also 10 to the 13 GeV. Alternatively, you can couple your scalar fields here. I've written many of them, but then the next slide it'll just be H again. You can conformally couple them to the curvature. So you can start with your Starobinsky. Delta here is either 0 or 1. So we were looking at whether or not you're doing just pure r squared or r plus r squared. So delta is just 0 or 1. So you can couple your matter fields this way. Now you do the conformal transformation, which is a little bit different. Before it was just this delta plus 1 plus 2 alpha phi. Now you would have to include the phi squared contributions because it's also multiplying by r. So you're just doing that. And then you can, again, do the machinery. This is actually one step earlier. So when you do the conformal transformation, you still get something that doesn't look quite canonical. And here are your additional matter fields, now with the conformal factor on the kinetic terms and the conformal factor on the potential terms. And this potential term is what gives you Starobinsky. It's this phi squared. Okay.
So, question about the previous slide, the phi decay Higgs.
Oh, here.
And in the potential term, if the Higgs doesn't have thermal mass, we have a thermal gap, and then that can be important.
Well, there's to start with, there's no temperature, there's no thermal mass yet.
Okay, so this decay assumes there's no.
Right, there's nothing.
Okay, that's true. That
Right.
means the
Right. So here, okay, same thing. Now generalizing it, putting in a conformal, just a general coupling to curvature of the Higgs. So the same thing. Before I had this to be a sixth, and now you do the same thing. You end up with your Starobinsky potential, which is sitting here. You get additional contributions coming from the Higgs. Okay, this won't really affect inflation because this is going to give you. It's just going to be negligible. And then here you have the coupling to the Higgs and the coupling.
This is not Higgs inflation.
This is not Higgs inflation, no, because this is phi is driving the inflation. So you do it all again, you get another decay rate. The only difference is now it's 1 minus 6 psi. Okay, so you have to remember that. So if psi is a sixth, this thing will just vanish. There's no decay rate at all.
Because of conformal symmetry.
Yeah, because of conformal symmetry. So, reheating, we always define reheating to be the moment where the energy density in the inflaton equals the energy density in the radiation. I'll get back to that a little bit more later. And then you can compute the reheating temperature, and now again you get this 1 minus 6 psi. Okay. There's also a coupling through the trace anomaly. So phi will couple to T mu mu. You can compute T mu mu, and you get another expression for the decay rate, and you get still a temperature. So even if psi is equaling to a sixth in the Starobinsky model. So the important thing here is that the typical reheat temperature in Starobinsky is 10 to the 9 GeV. It just comes out. And no matter how really that you, well, unless you conformally couple it exactly with a sixth here, but otherwise, generally, the order of magnitude is 10 to the 9 GeV. If for some reason you do make a cancellation there, you'll still get about 10 to the 8 GeV coming from the coupling to T mu mu. All right, so now let's make some comparisons. Let me just, yeah, okay. So if you remember, in the no scale, we had to do a conformal transformation where the conformal factor was related to the Kähler potential. In the r plus r squared, we're doing a conformal transformation which is related to the r plus r squared plus the conformal coupling, if it's there, to the scalar fields. When you add in matter, okay, which I just did, remember there was a phi squared term. This was coming from the conformal transformation, and this is what really gives you the Starobinsky potential. And then you get some other terms, v of h divided by that conformal factor. In the supergravity case, the v again gets a conformal factor, so that's effectively the e to the minus 4 omega, it should be. And so you get some v hat, which you would calculate based on the superpotential. I think I gave the expression earlier. And then you have the conformal factor. So you see there's a v over this conformal factor. If you associate t plus t star with 1 plus 2 phi, you're getting, again, the same type of things. This h squared would be all the other scalars that you might have in the theory if you set xi equal to a sixth. So there's a really strong parallel between the r plus r squared and the no-scale derivations of the potentials. I'm going to skip the thing on de Sitter. Let me go now to more specific on how you get r plus r squared in no scale. And so this was probably also 2013 or so. Wrote down something very simple, effectively just a Wess-Zumino model for some scalar field, the inflaton, phi squared minus phi cubed. And that will, in the no-scale context, lead exactly to the Starobinsky potential. So it's a little bit surprising. You start with your Kähler, which is t plus t star minus phi squared over 3. And with this superpotential, you get exactly Starobinsky. Don't worry about the forms with the y's. I think I'll mention it. It's exactly the same thing. It's just a field redefinition. There's an alternative. Actually, there's many alternatives. It's not unique. So there's one that was actually written down by Cecchetti probably in the late 80s, where he was doing a supersymmetrization of the r plus r squared theory. And he found this is the superpotential. In this case, phi is the inflaton. In this case, t is the inflaton. Okay. And these things can all be related, but I won't go through all of that. This is just the, so here's with the y, in the y basis, this is your Kähler potential. Here are the transformations. Okay, there's nothing very deep about this. It's just a field redefinition, and depending on how you want to write out the theory. So in the no-scale case, what about how does it decay? So if we're talking about phi inflation, it's like you're putting the xi equals to a sixth. And so in fact, if you try and expand everything out in the supergravity case, you'll find there are no couplings of phi to matter, which leads to a decay. I'm going to get to that in a second. So I said this shouldn't be surprising. The trace anomaly, okay. You'd say, now what is the coupling? The coupling should be k over 6 times t mu mu. And now you ask, okay, so now you take you have to expand this, but k phi is equal to 0. So there's no coupling from the trace anomaly either for the phi inflation. Okay. There is a way to still do it, but now you have to go beyond what I've been talking about, which is okay. You have to do something to the gauge kinetic function. You have to put in a coupling there.
Yeah. Can I ask a question?
Yeah.
Does that depend on some expansion of the exponential phi? That you only take the first term? What I mean is that, is there any phi squared t mu?
Oh, I'm not sure. That's a good question. I don't know. So the gauge kinetic function, so is it has to be, I mean, in principle you could just take it to be delta AB. Of course, if you did that, strictly speaking, you would get no gaugino masses. because the gaugino masses are determined by derivatives of the gauge kinetic function. Typically, you would put whatever field that's breaking supersymmetry in the gauge kinetic function, so that when you take derivatives of it, you end up getting gaugino masses which are related to your supersymmetry breaking parameters. Okay. Here you would have to, and in principle you can do it without upsetting anything else, you would have to put phi 1, I mix up phi 1 and phi, but phi 1 is the inflaton. It's one of the scalar fields that we select out to be the inflaton. If it's a function of phi 1, then you can again get non-trivial decay of the inflaton to gauge bosons and gauginos. Okay. And here M should be the supersymmetry breaking. Oh no, sorry, the M here, little m, I'm also mixing up little m and big M. This is the inflaton mass. It's relative to 10 to the minus 5. So you can again get reheating temperatures of order 10 to the 10 GeV. But this is now completely adjustable because you don't know what that coupling, you don't know what this thing is. So it's more or less free up to about that point. You could, of course, go a little bit farther, and you can associate phi with the right-handed neutrino. And so you can then would have a coupling, direct coupling in the superpotential to standard model fields, and then you would again get a lifetime which is fairly substantial. In this case, you can get reheating temperatures up to about 10 to the 14 GeV or so. Okay, if T is the inflaton, then there's all sorts of possibilities, but there are direct couplings. So this is the mu parameter. So there's only so many letters that get recycled. This is the regular supersymmetric mu parameter, so it should be of order TeV or so. So this gives you very low reheating temperatures. You can do a little bit better looking at the three-body decays. All of this can be written out. So once you have the theory, you can calculate what you actually get. You can also do the same trick with the gauge kinetic function. In this case, you will get decay through the trace anomaly because kt is the derivative of k with respect to t. That will not be 0. All right, so that was sort of the first half of the more formal things. Now a little bit more practical. So what happens as inflation ends? So here I'm starting with the Starobinsky potential. So the last 50 or so E-foldings, when we talk about E-foldings and we say 40 or 50, that doesn't mean that that's the total number. Because if the field starts out here, you'll have millions of E-foldings. You don't care about them because they're all still way, way out there. You only care about the last set of them, and that set is fixed by the scale on the sky usually, so that's this K star, which is chosen to be 0.05 inverse megaparsecs. So inflation ends, so by that, when the slow roll parameter epsilon is about order 1, or the accelerated expansion A double dot is 0, that's when inflation ends. And so typically, when you're calculating n, you'll want to integrate it just from here to here, and that will determine for you n. And then the field starts oscillating about its minimum. Okay, so it's all, oops. Oh, okay. And so equations of motion, this is an old story. So if m squared is very small, you can do an approximate solution to the evolution of phi, so along the flat part, and so when m squared is much smaller than h squared, this will be a valid solution for a time period which is given by that, and so long as m squared is much smaller than h squared, you can get plenty of inflation. Okay, so that's just the basic idea behind that. But what happens afterwards? So the solution, again, you can get a solution to the equations of motion during the oscillations, and that's just given, it's just a harmonic oscillator, a damped harmonic oscillator. And if the inflaton couples to standard model fields, at some point it has to in some way, because you have to get this, a thermal bath of standard model particles. And so if there's a decay rate, this thing will decay and get you reheating, and we'll see, gives you particle production. So again, we start with the same equations of motion here, either written in terms of the energy density and the pressure. So this is just convergence of T mu nu, and there's phi double dot in terms of the field. If there's a decay term, so I'm going to just parameterize the decay. So this is this y that I had y equals 1 before. Just to, actually, that's not a actually very good way to do it, but it's okay. It's easy to understand. Just that there are no standard model particles you can write like this. So, you think about it for a little while, you'll see why. It looks nice, and then you just see it and you accept it. But yeah, it looks okay. It's not. I can put, if I put scalars here, it would be okay. But think about which fermions in the standard model you could actually write this way. Huh? Yeah, it's gauge invariant. But it looks nice. It's simple. You could put a right-handed neutrino there. Before. Yeah, this is way before. It doesn't matter. It doesn't matter. It's just qualitative. It gives you a picture of what's going on. So now you have to adapt the equations of motion with the decay rate, and so you have now the one for phi, d rho dt. So that was this one. Now you have the appearance of radiation. So this is just the d rho dt difference between 3 and 4, just the equation, the difference in the equation of state for matter and radiation, and then you have the constraint coming from the Friedmann equation. Okay, and W is here. W is P over rho, and K. I'll define K in a minute. K will have to do with the shape of the potential about the minimum. So for K equals to 2, we're talking about a harmonic or the quadratic potential, and then at W is 0. So you can now, if the decay rate is small, you can solve these equations. You can actually solve them analytically, which makes it, I think, for me, more fun. And so this is, I still didn't define K. It'll be defined next. But it's what I told you. It's if you expand the potential about its minimum, this is assuming phi to the K. So here the energy density is dropping off some power of A, and if K is 2, you'll see this is just 3. So it's just going like matter, 1 over A cubed. This is with the universe expanding. I already said inflation ends when epsilon is about 1. Then there's subtleties on which epsilon you're talking about, epsilon derived from the potential or epsilon defined in terms of the Hubble parameter, and they're related to each other. So inflaton will decay when the lifetime of the inflaton is of order the age of the universe, or where gamma is approximately equal to h. And the radiation density is just given by alpha t. Alpha is just g pi squared over 30 here, alpha t to the 4th, when that's equal to the energy density in the inflaton, which is approximately h squared and Planck squared. There's some factors of 3 running around. And that's then equaling to gamma squared and Planck squared. So just order of magnitude, you see that the reheating temperature is of order gamma and Planck to the 1/2. And if you do it more precisely and you put in this gamma, then you get about 10 to the 15 times this y, where I've normalized to the inflaton mass, which is correctly normalized to the CMB. So here's how it looks. So this is the same solution we had before. Here's the solution for the radiation density. And as I say, you can do it analytically. This is A end, the value of the scale factor at the end of inflation relative to A reheating. Typically, A reheating is much larger than A end. On this particular plot, you see this is A reheating is here, A end is 1. So this is an absolutely tiny number, so you can even forget that. Don't look at that. And then this part is not completely trivial. Later on, it's not important, so the radiation density just really scales this. This part is important for the rise. So there's a very rapid rise, so we're looking at this curve now. From the solution to the equations of motion, you get a huge increase in the temperature initially. It's still now much smaller than the inflaton density, so it's not dominant, but there's a lot of energy density, typically This will be about 10 to the, it could be 10 to the 10, 11, 10 to the 12 GeV, depending on what the energy density, what the reheating temperature is. And then it falls off. And it falls off if you plug in k equals to 2 here. You'll see that for k equals to 2, the radiation falls off only as a to the minus 3/2, not as 1 over a to the 4th, which is what you would normally expect. Okay. Why? Because while all this is going on, you're always adding more radiation into the system. The inflaton, exponential decay doesn't mean the decays all happen at the age of, at the lifetime of the inflaton. You get a little bit of decays exponentially bleeding in, and you don't see it here a little bit. You start seeing this downturn this is where the exponential downturn comes. So this is where you would really decay. And so a lot of times people do instantaneous reheating. They just worry about this one point here, right? Because you can, and for many purposes that's fine, but it sort of ignores all the rest of this.
So at some point you have to go like 8 to the minus 4.
Absolutely. Here you start to see the shift. Right, so when this goes away, this will start to go as a to the 4th because you're not putting any more into the system. All right, so here, why do we see something in the back?
It's some memory effect on the screen.
Yeah, it must be your system. It's not on my slides. Have you seen that before? No? Okay. All right. So forget the bottom. These are different models. They're called T models. Well, actually, you don't have to forget them because I'm actually going to use them in a minute anyway. T models are how you can get other values of K easily. This is Starobinsky. It says alpha Starobinsky. Alpha equals to 1 is here. This is what I was telling you before. The alpha, it comes in the Kähler potential if you change minus 3 log to minus 3 alpha log. You're essentially changing the curvature of the manifold. Instead of 2/3, it's 2 over 3 alpha, and this thing will depend on alpha. Basically, R is sensitive to alpha, NS not so much. But anyway, you see that the model with alpha equals to 1 is still is what's good. This is the plot. I think that it doesn't have the formula, but I can still, yeah, it must be.
I think it's a memory effect of the screen.
Yeah. Of this screen itself, of the projector. Yeah. Or your.
I never saw that.
Okay. Yeah. All right. So this is this business about the relationship between N and T reheating. So this is the number of E foldings when you fix the scale at 0.05. There's then a relationship between NS and N, and this is the reheating temperature. This is coupling that gives you that reheating temperature. So here you see if I take Y of 1, I'm only going to get a maximum of about 55 E foldings. You can't get up to 60. And that gives you the value of 0.965, which is presumably this point right here. Well, it's not quite, oh no, that's 1, so that would be right here, actually. So it should agree with the other plot. And so you have to compute N self-consistently. I'm sorry I didn't write down the expression. I mean, you can find it.
You translate the N, heating to the required N.
Right. It's because, yeah, it's a self-consistent solution. You can't actually do it analytically. You have to do it numerically. And so anyway, here you get the range of N's that are allowable by the CMB observation. So you want to be, this is the 2 sigma lower limit on NS, so you need to be above there, which means you have to have reheating temperatures larger than that.
So Y is a proxy for the width, basically.
Exactly. That's all it is. That's all it is. All right, so particle production. So here, this is again, it's a somewhat older story. This is a lot of times called freeze-in. So here I'm just assuming that how you're producing particles during reheating from the thermal bath that's being created. So I'm saying that the cross-section to produce some particle chi is given by t to the n divided by some scale. And so the rate per unit time and volume is then t to the n plus 6 coming from that. So this is the radiation bath that's developing. You get a new Boltzmann equation, which you can then again solve and actually solve analytically. Okay. Again, most of this you don't care about. This is different values of n depending on k, and so these are just all numbers. So this is just numbers, but what you care about is the scale. It's T reheating here to the n plus 4. What's more important is that for larger values of n, you see that the maximum temperature comes into this calculation, and for still larger, here it's still logarithmic, but for larger values it becomes much more important. So let me just back up to this slide. So the T reheating was here, but for the larger n's, you care about all of this, and for very large n's, you care only about that. Okay. So if you're doing instantaneous reheating, you lose all of that. Okay, this is again just an informational slide. This is just a quick way of how you get omega h squared today. If you know what rho reheating, the energy density of your particle at the time of reheating divided by the reheating temperature cubed. Very simple thing that you can remember. You just need to calculate that. You need to know that. And then it's just 6 times 10 to the 6th. Okay. So some examples. So this is with n equals to 0. That would be like for a gravitino, just a regular supersymmetric gravitino. Lambda would be just m Planck. You get the standard result that the n over n gamma for the gravitino would be just related to T reheat over m Planck. It's a result that's been used since 1983, so nothing new there. And that you get, for 100 GeV gravitino, you get omega h squared about 0.1 for about 10 to the 10 GeV reheating temperature. That's where that limit on the reheating temperature, and that's this line here. Okay. So you would be looking at, for the gravitino, you'd be looking at around well, right about the top here, and that would give you about the 100 GeV mass to get omega h squared to be about 0.1. Okay. So that's fine, the general expression works. So another one, say, there are more. The n equals to 2 would be some mediator exchange. N equals to 6 is interesting because that would correspond to, say, the production of a gravitino in high-scale supersymmetry. So in regular supersymmetry, when gravitinos are produced, they're singly produced, usually with a gluino in the final state. But in high-scale supersymmetry, you're assuming that the gluinos, everything else is heavier than the inflaton, so you have to pair produce the gravitinos, and that causes the power to go up just dimensionally. The lambda is now m3 halves times n Planck, and now you would get, so n equals to 6, the T max becomes important. And so for T max of about 10 to the 12, T reheating of about 10 to the 10, you need a gravitino mass of about 1 eeV. Okay, so different picture. But all of this works into that same scheme, is that you're calculating the particle production during the reheating process. Of course, you can also have other mechanisms where the inflaton directly decays to your dark matter particle, and then, okay, it's a different calculation. But don't go to. So let me come now to we call gravitational portals. So another way of producing both standard model and dark matter. And here we're just relying on the gravitational coupling of all the particles. So we're writing out, so starting with R, just expanding it and writing out the perturbation of the graviton in this case. Here, the normal expansion is that. This is not canonical. There's some factors of 2. This H is canonical, and this H will couple to the energy momentum tensor for everything. So standard model, the inflaton, X, whatever you have, you'll always have this coupling. So that's inevitable. And from this coupling, you can start making diagrams that look like this. You can either have inflatons going to dark matter, inflatons going to standard model, or standard model going to dark matter. Okay, and this is just textbook. So, okay, this is what I said. You can have these three different cases. And as I say, here what we're going to consider is purely model independent, sort of, because you have to specify the inflaton. So it's not completely model independent, but the couplings are model independent. They're just gravitational couplings. So standard model to dark matter. So this standard model is the standard model that we just were talking about during the reheating process. You're building up the radiation density, and it's now scattering through gravitational processes to make the dark matter. Okay? Rather than putting in this sigma v of t to the n over lambda, we're just using gravity. So throw that other thing away and just use gravity. You can again calculate n, you can calculate omega. This is actually usually pretty small. Because T reheat over M Planck here cubed is going to be a small number. You can make MX big, that will help compensate a bit, but this is not going to be a dominant source of production. You can do the inflaton directly to the dark matter. You do the same procedure, you can calculate omega, and now for k equals to 2, you get something that looks like this. And that's the red curve there. So for 10 to the 7 GeV dark matter particle, this is assumed to be a scalar now, T reheat of 10 to the 10, you would get the right relic density. So this is already scaled to 0.1. So that's this line here. K.
There's no Planck suppression there?
What? There's no
Planck mass suppression in this case?
Oh, it's in all the numbers.
It's all in the numbers.
Well, yeah, there's, where is the, here, even there, it's already been built in. There's a 2.4 times 10 to the, I mean, it's evaluated, it's already evaluated, yeah. Of course, the rate is Planck suppressed.
Yes.
So, but here it's just evaluated already, numerically evaluated.
How does it compare with the previous one?
Well, it's two different, this is much, much larger. I had more detailed slides. No, this is much, much larger.
Why? It's also gravitational.
Why? Because now, yeah, it's gravitational, but the energy density in inflaton is much, much larger than the energy density in that radiation bath, right? It's only at reheating that the radiation becomes more dominant, but this is happening at the onset, right? Right at the beginning of reheating, not at the end of reheating. So the energy density in the inflaton, as you see, there's a rho phi here.
Yeah.
And the rho phi squared is much bigger than anything else. So you have, coming out of inflation, you have this immense source of energy that's in the inflaton. Now, what you should ask, what do I mean when I'm doing k equals 4 and 6? So k equals to 4, you have a quartic potential, so they're not harmonic oscillations. And even the whole idea of how you're doing the Feynman diagrams, you have to be careful because the expansion is not, you shouldn't do it that way. And we don't, but I don't go through the details. If I was only talking about this, I would, but you actually have to treat the oscillations and do a Fourier expansion of the oscillations and look at the actual production of the particles. For k equals to 2, you can go back to your intuitive way, which is the way I actually always calculate it. It's using the Feynman diagrams. I let everybody else compute it the more rigorous way. But you get, for k equals 2, you get the same answer.
The non-instantaneous reheating is taken into account.
This is all non-instantaneous. Yeah, you would never get this for instantaneous reheating, because this is not instantaneous reheating. You're never sensitive to that initial burst of energy. It's all coming very late, and it would be much smaller. And this is for fermions. So you get something similar. Again, M Planck is there to the 4th power in the rate. So, but it's and that these curves. And so first of all, you're pushed to much higher masses. One is because you have helicity suppression for the fermions, this mx over m phi that you didn't have for the scalars. And if you're wondering about this bend is actually where the other one actually does become important. You're at very high reheating temperatures, and at that point, the bath particles will be more important than this gravitational production, because you're now going to lower masses. You're getting suppressed here at higher temperatures, which is augmenting the other one. So you can't forget about it. And this one, I guess I don't say much about this one. You can imagine, can you do the reheating directly this way? So here, looking at the production of Higgses, which then thermalize and get you the rest of the bath. So there's effective quartic coupling between phi and H. So that coupling you can write, again, it depends on the energy density in the inflaton, and you can compute the energy density that you're getting that way. So what that curve is this one. So I didn't explain this one before. This is, and you'll notice this one does fall off as 1 over a to the 4th. Because you're producing the radiation from this mechanism in a burst, and then that's it. It just shuts off, so the radiation density falls off like 1 over a to the 4th. And here, okay, this is a value of y, which is 10 to the minus 8. Y will control this lower one. So if I increase y, this will go up. So I've picked one where this peak is dominant. Okay. And you can ask whether or not all of the radiation can be produced from this. Well, you can already see from this plot, the answer is no, because this is falling like 1 over a to the 4th, this is falling like 1 over a cubed. It will never lead to the reheating. But for higher values of k, the inflaton behavior will be different. Remember, it was going as 6k over k plus 2. For k equals to 4, this is going as 1 over a to the 4th, so they'd be parallel. Still doesn't work. But for k equals to 6, it will actually go as a to the minus 9 halves. And so you can actually get all of the reheating coming from the gravitational production. Yes and no. You actually have to go to non-minimal. And I'm going to skip the non-minimal. It's not, I even pulled it out in advance. Just want to say a few words before finishing on this business with the fluctuations. This is a little bit what I was telling you about earlier. So I'm imagining I add an additional scalar field. Phi is now my inflaton. Just having a normal scalar field, just a mass term, no self-interactions. The only interaction I'm having is a potential gravitational coupling of the field to phi. Now, it's not really the one that I showed you before, even though I expressed it this way. On shell, the other one wouldn't lead to this. The other one is correct on shell, but you wouldn't get this interaction directly from the single graviton exchange. But let me suppose that you have this interaction for wherever it comes from. I'm not going to worry about right now where it comes from. So I have an effective mass squared for this chi when phi has an expectation value. So during inflation, the effective mass of chi is large. Okay. And I can now solve the equations of motion. And now I care about 4 scales. I care about the end of inflation. I care about when this thing starts to oscillate. I care about when eventually this becomes small and I become dominated by the bare mass. And I care about the reheating scale. And AN is usually the first one. But after that, I can shuffle around the other 3. Okay. The other thing is what happens to chi. So during inflation, and this is an old story, as I say, it goes back to Bunch and Davies, Vilenkin, the chi squared will grow linearly in time. It will grow as h cubed t up to a maximum value, which is given by h to the 4th over m squared. Okay. And this could be much, much larger than h if m chi is small, or m chi effective is small. Okay. So we're going to use that as our initial condition for chi squared. And chi squared, as I said, satisfies the same equations of motion as a regular scalar field. And so I have something that looks like this. Rho of chi as a function of the scale parameter is just going as m chi squared times chi squared. Now this is the effective mass, so this includes the interaction. And if this is dominant, if sigma phi squared is large, then I can work out the scaling, and I get, instead of it just going as 1 over a cubed, it will get an additional piece, and so it's going as 1 over a to the minus 9 halves for a limited amount of time. And again, in this case, you can work out everything analytically. I know you're going to be blinded by the equations. It doesn't matter. But you have a oscillation relative to a chi. That's where the a chi is, remember, where the bare mass becomes dominant. So you can shuffle these around. And you get conditions on the coupling. Everything will just depend on what the value of this coupling is. So that will determine, and here I've scaled the coupling, sigma tilde, I'm taking out the gravitational suppression, right? So this is a small number. Sigma tilde is order 1, this is of order 10 to the minus 10. So we're always talking about a very small coupling that we're adding in there. And you can work out then how does the energy density evolve in time. Here, this is rho times a cubed. So this is actually a constant energy density. This is growing here as a cubed. And then it starts to oscillate, and eventually you have reheating. Okay? And you can again then work out what the value of omega h squared is. Now, so this is somewhat severe. This is with a very small sigma. So this is with sigma essentially negligible. You need a mass of around 10 to the 12 GeV and a reheating temperature of only 70 GeV to avoid overclosing the universe. And that's because now there's so much energy that's been stored in the scalar field due to these fluctuations. Okay. So you need to damp it with the mass and keep the reheating temperature down to keep the amount of energy relatively small. You can then combine that with the gravitational production, and you get a very limited range in temperatures. So reheating temperatures up to about 4 TeV. This is just the BBN limit of 4 MeV. So you have a very limited range in allowed reheating temperatures, and limited range in the masses, somewhere between 10 to the 10 and 10 to the 13 GeV. That's all you can have. For a stable scalar, where its initial abundance is coming from these fluctuations, and no self-interactions, which is a key. And here I've ignored the gravitational interactions as well. So, and it turns out then, once you increase sigma, so now you're adding this coupling. So here we don't treat the self-interactions, but this is adding the coupling of the scalar to the inflaton. Even 10 to the minus 10, order 10 to the minus 10 couplings, it changes the picture completely, because now this sigma gives you an effective mass, and that effective mass then cuts off these oscillations. Remember, it's h to the fourth over m squared, but if m squared is now big, you don't get this huge amount of energy density. And there's actually an exponential suppression in chi squared, and that then allows you to have a wide range in temperatures and as a function of these couplings for different masses. So, okay, I skip these details maybe and go to this plot. This plot has, so this top line, this didn't show up. No, it's not on my slide either. Okay. This should be the dashed line up here. This is the same line that I showed you before for the gravitational production. And now you can have, from the couplings to these fields, you can change your result. And so this is what I had before. Well, this is what you have now. This is now, so it should be compared with this is what I showed you before. Now you have a huge range in allowed masses from down to, was that 30 MeV up to 10 to the 13. This is just the kinematic limit. And you have a wide range in temperatures for a relatively small variation in these couplings. So it's very sensitive to this coupling. This is, remember, this is in units essentially of 10 to the minus 10. 10 to the minus 10, 10 to the minus 11 coupling.
So the lower bound of chi comes from requiring that the reheating temperature is less than the Planck mass or something like that?
Not less than the Planck mass, less than the maximum that you can reheat to, which is if you want a perturbative decay. So the reheating is still taking place through the decays. So that's it. I just want to make this figure. If I did do something like non-minimal coupling to gravity, so put in some conformal coupling of these fields, I would generate the same type of quartic couplings. And so I could replace this sigma with the psi, whatever the psi is, coupling of curvature to the scalar field, and I would get this sort of similar pattern, almost identical. Anyway, I think that's all I wanted to talk about. So we went through a lot of things, just starting with the Starobinsky model, which fits the data as well as can be expected. So that's why, as I say, a lot of concentration is being placed on that type of a model. Whether you're talking about r plus r squared or deriving that from supergravity, and in particular no-scale supergravity, there are a lot of parallels which I find interesting beyond that. As I said, reheating is obviously an essential component of any model. The model is not complete unless you have some mechanism to reheat the universe, and it's important not to be focused only on instantaneous reheating, which, although in some cases, like the original gravitino production with n equals to 0, instantaneous reheating will give you the right answer. If that's all you care about, that's fine. But there's a lot more there when you really take into account the early phases of reheating, whether it's this kind of freeze-in production when n is greater than 6, or looking at the effects of the gravitational production that is using only the gravitational interactions, or looking at these scalar field fluctuations. All of that's going to be very sensitive to these initial stages of reheating. So I'll stop there.
Thank you. Questions for Keith?
No, there's questions during, so.
I have a question.
Okay.
So, it's about the K.
Which K?
The K that is the minimum.
Okay, the little
power
K.
of five,
Okay.
little
Okay.
K. The Starobinsky model is fixed, or
K equals to 2.
the Starobinsky is K equals to 2.
Yeah, K equals to 2, so it's quadratic about the minimum.
So it's
So
dark matter.
these, it's like matter. So the T models, you can, which I didn't write anything down. I don't know if I can find. Yeah, the T models you can also.
Play with K.
Yeah, you can, especially if you start from the supergravity point of view, you would have, it's always phi to one power minus phi to another power. For Starobinsky, it's phi squared minus phi cubed. You can get the T models using different powers. Again, subtracting two different coefficients, and then you'll get a potential that looks something like a hyperbolic tangent to the K. And hyperbolic tangent is like a symmetric version of Starobinsky. So you would have Starobinsky on both, you'd have two plateaus coming down, and with tangent, hyperbolic tangent to a power will change the shape at the bottom. And then it'll be phi to the K when you do the expansion. It's not as nice as K equals to 2 is sort of the standard nice thing, but you got to keep busy.
Yeah.